Ever look at a wiring diagram for like a plane and think, wait, how does this even work?
It can look like a total mess.
Yeah.
That's why today we're diving into the world of electrical circuits.
Okay.
We're using this recent quiz on basic electricity as our kind of our jumping off point. And I gotta say, there's some really cool stuff in here.
Oh, yeah.
Like, did you know that how hot or cold something is can actually affect, the flow of electricity?
Hmm.
We're going to break that down, especially, how it works in aircraft.
Okay.
But before we get ahead of ourselves, let's back up a bit, talk about the fundamentals. What are the core components of an electrical circuit? What makes it tick?
It's kind of like imagine the nervous system of an aircraft, right?
Okay.
It's sending all these signals everywhere. An electrical circuit is essentially doing that.
Mm-hmm.
But instead of, nerve impulses, we're talking about the flow of electricity,
Right.
right?
So it's all about keeping that energy moving. But it can't just be like a free-for-all, right? There need to be some rules, some kind of structure to it.
Right.
So what are the key pieces that make sure everything's playing nice together?
Yeah, so just like any well-organized system,
Yeah.
an electrical circuit needs a certain set of essential elements.
Right.
Think of them as the core crew on a flight.
Okay, I like that.
Yeah.
I'm intrigued now. Who are these VIPs of the electrical world?
Well, first off, you got to have a source, right?
Okay.
The powerhouse providing that electrical energy. That could be a battery, a generator, could even be something as simple as just plugging into, your wall outlet.
Right. Every operation needs its fuel, its energy source.
Yep.
Okay, so what's next? What else do we need?
Next, you need a way for that electrical energy to actually travel.
Okay.
And that's where conductors come in.
Conductors.
These are materials, and we often see them as those copper wires, that allow electricity to flow super easily.
So the conductors are like the arteries and veins of the aircraft's electrical system.
Yeah.
They're what carry the electricity to where it needs to go.
That's a great way to put it.
Now, just like a nervous system, right, sending all those signals to different parts of the body, an electrical circuit needs a target,
Okay.
needs something that's going to use that electrical energy. And we call that the load.
So the load is like the destination.
Exactly. And those destinations can be anything from the avionics buttons to the lights in the cabin, even down to the coffee maker.
Right.
Anything that runs on electricity in an aircraft, that's a load.
Okay. That is making a lot more sense now.
So we've got the source, conductors, and the load.
Right.
But didn't you say there were 5? What about control and protection?
Yes. And those are crucial, especially when we're talking about something as complex and potentially hazardous as an aircraft.
Right. Okay. Those sound important. So let's talk about control first. What's the key player there?
So the control element, that's like the air traffic control of our electrical system, right?
Okay.
It's directing the flow of the electricity, making sure it goes where it's supposed to go and doesn't cause any chaos.
Right.
And that's where switches come in.
Switches, right?
Specifically toggle and rocker switches,
Yeah.
which are super common in aircraft.
So like a light switch on your wall.
Exactly. A light switch, that's a great example of a simple switch, technically called a single pole, single throw switch, or SPST.
Okay.
But in an aircraft where you've got all these complex systems that need more precise control, you often find more sophisticated switches like double pole, double throw switches.
Double pull, double throw.
Yeah.
DPDT. Okay.
DPT.
What makes those so special?
Yeah.
Those sound intense.
Think of it this way.
Okay.
A basic SPST switch, it's like turning a light on or off.
Right.
It's a very simple on-off command.
Yeah.
But a DPDT switch, that's like having 2 of those switches linked together, giving you the ability to actually control 2 separate circuits at the same time.
So it's like multitasking for electrical circuits.
Exactly.
That's got to be super helpful in a plane where everything's like, interconnected. Can you give me an example of how that might be used?
Absolutely. Imagine you've got, a critical flight control system, and you need a backup power source,
Right.
a DPDT switch, that could be used to instantly switch from that primary power to the backup if something goes wrong,
Wow.
ensuring that system never goes down.
So they're like silent guardians, those switches, just like ready to jump in.
Exactly.
Wow.
And that actually brings us to the importance of our 5th element, which is protection.
Right.
Just like an aircraft has all these redundancies, all these safety features built in to prevent accidents, electrical circuits, they need safeguards too.
Right. To prevent things from getting overloaded. Okay.
Overloaded short circuits, exactly.
Makes sense. So what are the heroes of circuit protection?
Is it fuses and circuit breakers?
You got it.
Okay.
Fuses and circuit breakers. Those are
Yeah.
like the safety valves of the electrical world.
So if something goes wrong, they're the ones that step in and
Yeah.
kind of like hit the brakes to stop a total meltdown. Tell me more.
Right.
Okay, so they're like the emergency crew, just standing by, ready to jump in if anything goes wrong.
Oh.
How do they actually work, though?
Yeah, so a fuse, for example.
Okay.
It's designed to be the weak link in the circuit,
Right.
right? It's
Right.
just this thin wire inside, and it's calibrated to melt and break the circuit if that current gets too high.
So it's like a self-sacrificing hero taking one for the team to protect the rest of the circuit.
Yeah. And just like you'd need a new hero, for each threat, you got to replace a blown fuse. A circuit breaker, though, that's more like a reset button.
Okay.
It trips open when it detects an overload, but then you can just reset it once you fix the problem.
So a fuse is like those emergency fire suppression systems that just flood a whole room, and a circuit breaker is more like a regular fire alarm. It's like, hey, something's wrong. You should probably get out of here. But then you can reset it once the danger is past.
Yeah, that's a great analogy. And you see those reset buttons all the time.
Yeah.
Remember, we were talking about that circuit breaker panel earlier.
Right.
Those switches that you flip when there's an overload, those are your circuit breakers in action. Once you figure out what caused it, like, too many appliances running or whatever, just reset it and you're good to go.
This is all making so much more sense now.
Oh.
But going back to our source material here, there was this part that mentioned that you shouldn't use automatic reset circuit breakers for circuit protection in aircraft.
Right.
Only trip-free breakers.
Right.
What's the difference? Why is that distinction so important?
That's a great question, and it really gets to the heart of aircraft safety. So a trip-free breaker, it stays open even if someone tries to reset it while that fault is still there.
Okay.
It's like having a safety system that you can't override, even by accident.
So it's like having a second set of eyes,
Yeah.
like a co-pilot who's double-checking everything, making sure it's actually safe before anything comes back online. Like, no risks here.
Exactly. And in aircraft, you can't risk having a circuit breaker automatically reset before you've addressed the underlying problem, right?
Yeah.
Because even that momentary surge could have serious consequences.
Right, safety first, especially when you're miles up in the air. Speaking of safety, we were talking earlier about how, temperature can affect a circuit.
Right, right.
And our source material mentions that this same principle is actually used in some temperature measuring devices, which sounds kind of wild to me. How does that even work?
It's actually it's a very clever use of a very simple concept. You see, some materials, especially certain metals, they have this interesting property where their resistance to electrical current, it actually changes with temperature.
Hold on.
Yeah.
You're saying that, like, the hotter these materials get, the harder it is for electricity to flow through them?
Exactly.
Okay.
It's called a positive temperature coefficient of resistance.
Okay.
So if you pass a known current through a wire that's made of this type of material, the voltage drop across that wire, it'll change proportionally to the temperature.
So the wire itself is telling you how hot it is by how much it's resisting that flow of electricity.
Yeah, essentially.
That's wild. Where would you even use that in a plane?
Oh, all over the place. Think about, your engine temperature sensors.
Yeah.
Or the systems that monitor the temperature of those really critical flight control surfaces.
Okay.
A lot of times, these rely on this very principle. By measuring the resistance of a specific component, you get a real-time reading of its temperature. And that is obviously crucial for maintaining a safe flight.
It's like having this network of tiny little thermometers just like embedded throughout the entire aircraft, all because of this connection between temperature and resistance.
Yeah, it's pretty amazing.
That is really cool.
And it doesn't even stop there, right?
Okay.
Remember when we were talking about resistors and how they kind of act like the brakes in our electrical system?
Yeah.
Well, this temperature dependence, it actually plays a role there too.
Wait, are you telling me that those tiny components, the ones that we were talking about, that they're actually affected by temperature too?
It's true.
Okay.
But while we often think of resistors as having this fixed resistance, but the reality is it's a bit more nuanced than that, especially when you're talking about environments like in aviation that are just so demanding.
Okay.
Changes in temperature, they can slightly alter their resistance.
Okay, so it's not like they're going to just stop working completely because they get a little bit hot. But it's just something that engineers need to be very mindful of when they're putting these systems together.
Absolutely. Yeah, it's all about precision and reliability.
Right.
Especially in aviation, right?
Right.
You can't have a critical system malfunctioning just because, there was a slight change in resistance due to some, temperature variation.
Right. Makes sense.
Yeah.
Wow. It's amazing how even these tiny little components, they have to be designed with so much care and attention to detail.
Oh yeah, it's a testament to the engineers who design these things.
It really is. And speaking of those engineers, I'm assuming they have some tricks up their sleeve for dealing with these temperature challenges.
All right.
It's like there's got to be a way to make those resistors a little bit tougher, a little bit more resilient, especially when things start to heat up.
Yeah.
So what's the secret sauce? How do they do it?
So what's the secret sauce? How do they do it?
Well, they've got a few tricks up their sleeves. One approach is, they'll use materials with a very, very low temperature coefficient of resistance. Remember, we were talking about how some materials are way more sensitive to those temperature changes than others.
Right, like those special metals that are used in the sensors.
Exactly. So for resistors that are, in those really critical applications, you want the opposite.
Okay.
You want materials that basically don't even flinch when things heat up.
Okay.
So they might use, special alloys or even ceramics that maintain a really stable resistance over a pretty wide range of temperatures.
So it's like they're giving those resistors like high-tech thermal gear.
Right.
They're basically immune to like scorching engine bays or, being way up high where it's freezing cold.
Yeah. And sometimes it's not even just about the material itself, it's how they put it all together. So they might use things like heat sinks, which are designed to pull that heat away from those sensitive components.
Yeah.
So kind of like how those cooling fans in our computers, they keep our processors from like melting.
Exactly.
Okay.
Yeah. Those heat sinks are like little radiators. They just dissipate the heat and keep those resistors running cool under pressure. And in some cases, they even use, active cooling systems, like think tiny little fans that are circulating air, making sure those temperatures stay exactly where they need to be.
Wow. So they really put these little components through the ringer to make sure they can handle anything, huh?
Oh, yeah. It's all about precision and reliability, and especially in aviation, they really go the extra mile.
It's incredible. This deep dive it's really eye-opening,
Yeah.
Going from those basic circuit diagrams to like the intricate world of switches and resistors and temperature sensors and safety systems all working together to keep those aircraft up in the air. It's amazing.
And let's not forget the unsung heroes of all of this, right?
Yes.
The electrical engineers who make all of this possible.
They're the ones who, like, they speak the language of circuits.
They do.
They understand how it all works, and they make sure every single connection, every component is up to the task.
Yeah.
It makes you appreciate just how much goes on behind the scenes when you do something as simple as like flipping a light switch or adjusting the temperature in your car or on a plane, right?
It really is incredible. It's a testament to human ingenuity, wouldn't you say?
Absolutely. It makes you realize that even the most high-tech stuff out there, it still comes down to these fundamental principles of physics,
It does.
It's pretty amazing when you think about it.
It is, and it's something to maybe ponder the next time you're on a flight, right?
Right.
As you're getting settled in, getting ready for takeoff, just take a moment to think about that intricate network of electrical circuits working tirelessly beneath you to make sure that you have a safe and comfortable journey.
That's a great point. And on that note, I think we've reached the end of our electrical adventure for today.
But for all of you listening out there, remember, the next time you see a circuit diagram, don't freak out. Don't shy away.
Yeah.
Think of it as a map. It's a map to this fascinating world of energy and connections and incredible design. So until next time, keep exploring. Keep asking those questions. Never stop being curious about the world around you.